This is the 5th lecture on signals and systems, and the topic is basic concepts of linear time-invariant systems. In the process, we shall introduce the term convolution, which is one of the most important processes in the analysis of signals and systems. Before we come to the topic proper, I would like to recall what we did at the end of the last class. That is, we had introduced what are known as linear and nonlinear systems. And I said the strict definition is, formal definition, that if x1 of t leads to y1 of t, and if x2 of t applied independently leads to y2 of t, this is the system S, and this implies that if you multiply x1 by an arbitrary constant alpha 1 and superimpose this on alpha 2 multiplied by the second input, leads to the same type of multiplication and superposition of the outputs, that is alpha 1 y1t plus alpha 2 y2t. This is the formal definition of a linear system. If this is obeyed, then the system is said to be linear. There are two principles involved. One is superposition and the other is homogeneity. Both must be obeyed in order that the system is linear. Both must be obeyed. But if it disobeys one, you can throw out the system that it is not linear. All right. Again, the same principle. One counterexample is sufficient to disprove an assertion. 1,000 examples are not sufficient to prove an assertion. All right. So if you can prove that the system does not obey homogeneity, all right, it is not linear. You don't have to test for superposition. On the other hand, if it obeys homogeneity, you have to test for superposition also in order to see whether the system is linear or non-linear. But this general test, which incorporates both superposition and homogeneity, should suffice. We'll take one example before we go to formal characterization of linear time-invariant system. And this example is, we have a system S to whom the input is x1 of t and the output, it's an SISO system, single input, single output, and the output is given by minus infinity to 3t x tau d tau. We have to find out, we have to characterize this system. The first thing we ask is this a linear system? Is this linear? You see, if I apply x1 of t, then the output shall be y1 of t. If I apply x1, output is y1. If I apply x2, output is y2. So if I apply alpha 1 x1 of tau plus alpha 2 x2 of tau, then the output should be equal to this would be the output. And you can easily see that this is equal to alpha 1 y1 of t plus alpha 2 y2 of t. It's very easy to see. Linear. It obeys superposition, it also obeys homogeneity. The operation itself is a linear operation. The next question that I ask is minus infinity to 3t x of tau d tau. Is this a memory system or memoryless? Does it have memory? Yes, it does, because the present output t, yt, depends on all past outputs from minus infinity up to 3 times t. Therefore, it has memory. All right. Is it causal or non-causal? Non-causal. Why? Because of 3t. If t is equal to 1, the output at t equal to 1 depends on the input that shall be applied at 3, and therefore, is that clear? Is that correct? X of tau occurs here, and therefore tau varies from minus infinity to 3t, and if t is 1, then the output at 1 depends on what the input shall be at 3, and therefore the system is non-causal. The system is non-causal. Is this a time invariant or time varying system? Now, how do I test that? To test this, we apply the definition. We go to the roots and we say x of t leads to y of t, which is equal to integral minus infinity to 3t x of tau d tau. Now, if I delay the input by, let's say, t0, that's how we test time invariance. Then the new output, let's call it y prime of t, shall be equal to minus infinity to 3t x of tau minus t0 d tau. Is that right? All that changes is the input. The limits of integration are not functions of the input. They are functions of the system. They are parameters of the system. So the limit remains the same. T does not change here. All right. So this I can write as minus infinity to, let's put tau minus t0 as some variable z. Then I get x of z and d tau becomes dz. If tau is minus infinity, obviously z is also minus infinity. If tau is 3t, then z is 3t plus t0 or minus t0? Minus t0. All right. And this is not equal to y of t minus t0. If it was y of t minus t0, our upper limit should have changed to 3 times t minus 3 times t0. And therefore, this is not equal to y of t minus t0. In other words, the output is not of the same shape, and therefore the system is time varying. You have to be very careful about testing time invariance or time varying character of a system. Well, is it stable? Our relationship is yt equal to minus infinity to 3t x of tau d tau. Is this a stable system? Well, in order to test whether it's stable or unstable, you might have to think a little and apply some clever tricks. Here, for example, we apply that principle of honesty in human beings. Find one counterexample. If you can find one x tau for which the output grows in an unbounded manner, then we conclude that the system is unstable. The simplest that we can think of is, let xt be equal to a unit step function, ut. All right. Then what is yt? Yt becomes 0 to 3t, because unit step function does not exist for t less than 0, and ut is 1, therefore it's simply d tau. All right. So this is 3t ut. Is that right? If xt is ut, then the output is 3 times t Why did I multiply by ut? To indicate that the output does not exist for t less than 0. All right, and you see that this grows in an unbounded manner. This tends to infinity as t tends to infinity, and therefore the conclusion is the system is unstable. Is this point clear? All right. Okay. Finally, yt equal to minus infinity to 3t x of tau d tau. Is this an invertible system or not? That's the question. Is it invertible? Yes. If you differentiate, then dy dt, shall it be equal to xt?
One-third.
I leave that question to you.
One-third of the next differential.
I expect other answers. One of the answers is 1/3 of xt. What you are saying is dy dt is equal to 1/3 of x of
3 times of x of 3t.
3. One says 1/3, the other says 3. Is there any other answer? I leave this with a question mark. We shall clarify this in the tutorial class. The conclusion is the system is invertible. All right, we can get back the output. Now, if we get x of 3t, obviously that is not the input. What do we have to do now? If we get, let's say, by differentiating, let's accept that we get x of 3t. But it is not x of 3t that we want. What do we want? We want x of t. So what do? We make a time scaling. That's correct. And therefore, we have to make a transformation of the independent variable. But the fact of the matter is, we can get back x of t. And therefore, the system is invertible. Now let's come to LTI systems, that is linear time invariant systems. These are a study of linear time invariant systems is extremely important in practice because most of the useful systems can be approximated by LTI systems. Most of the useful practical systems can be approximated by LTI systems. L stands for linear and TI for time invariant. We are not attaching any other adjective. The system could be with memory or memoryless. System could be causal or non-causal. System could be invertible or non-invertible. System could be stable or unstable. We don't care. We are concentrating on linear time invariant. That is, we don't allow non-linear systems. We don't allow time varying systems. The reason why this is important depends on or hinges on the first letter L, that is linearity. Linearity says that the principle of superposition as well as homogeneity are valid, which means that given an arbitrary signal x, given an arbitrary signal x of t, if you can decompose the given signal x of t in terms of a large number of components, simpler components like this, let's say summation a sub I xit. A sub i's are the scaling factors that takes care of the homogeneity, and x sub I are simpler inputs, simpler signals. This is summed over I. Then obviously all you have to do is to find the output in response to the simpler signal xit. If this is yit, then obviously, and if the system is linear, then this would be simply because of the principle of homogeneity, it would be ai summation over I. This will be the output. Is that clear? And this is why linear time invariant systems are very simple to analyze. The basic tool is that the given signal is decomposed into various elementary signals, and then you find out the output response to the elementary signals, you multiply by the appropriate scaling factors and sum them up. That gives you the total output signal. And it turns out that the elementary signals, of the elementary signals, you can concentrate on just one of them. In the continuous time system, all you have to concentrate on is the unit impulse function. And in the discrete time signals, all you have to concentrate on is delta n. That is, now this is a very important statement that I am making, that if in a continuous time system, if a continuous time system, you know the response of the system to delta of t, a unit impulse function, let's call this h of t, then the theorem says that you can find out the response to any arbitrary signal x of t. All right? So just one elementary signal, namely a unit impulse function, if you can find the response to unit impulse function as h of t, then you can tackle any arbitrary signal x of t. Any arbitrary signal x of t produces a response which can be written as summation of ai h I t. All right? That's the basic simplification that you obtain for analyzing a linear system. In a similar manner, for a discrete time system, if you know the output due to an excitation which is an unit impulse function delta n, and if the output is h of n, then you can find out the output due to any arbitrary signal x of n. This theorem will be true if you can decompose the given signal x of n in terms of elementary signals delta n. All right? And you know how to do it. For example, let's take a simple example. Suppose I have 1 half minus 2, 0 is 0, plus 1 is, let's say, minus 1, and plus 2, let's say, is half. Suppose this is my signal. All other samples are 0. This is my sample. Can I write it as a summation of delta n's? Can I decompose this signal as a summation of delta n's? And it's very easy to see that x of n can be written as minus 2, take the non-zero samples only, at minus 2 it is half, so half delta of n plus 2, wonderful, then plus 1 delta of n plus 1 plus 0, then minus delta of n minus 1, then plus half delta of n minus 2. That's it. And therefore the arbitrary signal can indeed be decomposed into delta functions. And if you know the response to delta n, then you know the response to all the components, provided the system is time invariant. Because if you know the response of the system to delta n, let's say h of n, then delta of n minus n0, whether n0 is positive or negative should not matter. In a time invariant system, this will lead to h of n minus n0. And this is where the importance of time invariance comes in. All right? So let's recapitulate the importance of the two adjectives, linear and time invariance. Linear means that you can decompose the signal in terms of just one elementary signal, delta t or delta n. And time invariance means that if you know the response to delta n, then you also know the response to delta n minus n0. And a general signal x of n can always be written as x of k delta n minus k summation k equals minus infinity to n. All right? Any general signal can be written in this form. If we go back to the previous, you see that's what we did. This is x of k, x of minus 2, delta n minus k is minus 2, plus this is x of minus 1, delta n minus minus 1, and so on. I think I have introduced this summation earlier also. So this is my x of n, and if I know the response to delta n, then I know the response to any arbitrary signal. To show this in a little more compact manner, let's consider this simple argument. The textbook does it in a somewhat complicated manner. We will simplify this. Delta n leads to h of n, and if the system is time invariant, then delta n minus k leads to h of n minus k. This is the property of time invariance. And then homogeneity, one of the principles constituting linearity. If we apply homogeneity, if we multiply this signal by a constant x of k, you see n is our running variable, x of k is a constant, it's the value of the signal at a particular value of n equal to k. If we multiply this by n minus x of k, then the principle of homogeneity says that the output should also be multiplied by x of k. All right? And then if we superimpose all such signals, if we sum up all such signals, the principle of superposition says that the output should also be the summation over k. Now you notice that the left hand side is precisely x of n. The left hand side, this summation is precisely x of n. Any arbitrary signal can be written as a summation of such components xk delta n minus k, and therefore the output must be y of n. All right? And therefore I can write there's one confusion that I created. Let me refer to the previous slide. Does it matter if this upper limit is changed to infinity? It doesn't matter, because delta n minus k exists only at a specific value of k, specific value of n, that is n equal to k, and therefore the upper limit can be infinity. We shall use this upper limit k equal to minus infinity to plus infinity, then this is minus infinity to plus infinity. In other words, the output of a linear time invariant discrete time system to an arbitrary input xn is given by xk h of n minus k summation from k equals to minus infinity to plus infinity. And this summation is called the convolution summation. Convolution summation. And in order to make an imprint in your mind, let me write this again and again. I shall do that till you get saturated of this relation. Xk h of n minus k. This is the convolution summation, And it shows clearly that if you know the response of the system to delta n, then you know the response of the system to any arbitrary input. Now, this operation of taking xk, that is a particular value of the signal sample, multiplying by h of n minus k, which is a shifted impulse response. H of n is called naturally the unit impulse response, that is the response of the system to unit impulse, h of n. All right, x of k is the value of the signal at an arbitrary instant of time, n equal to k. H of n minus k is the shifted impulse response. You multiply the two and take the sum from minus infinity to plus infinity. This operation, which consists of 3 steps, choose a value of k, choose a value of n equal to k, shift the impulse response, multiply the 2 samples and sum them up over all possible values of k. This operation is known as the convolution operation, and the convolution operation is simply represented as x of n. What you are operating on are these 2 signals, x of n and h of n, and convolution operation is represented by a star between them. Whenever we write x of n star h of n, we mean this particular summation. This is called convolution summation. The operation is called convolution, and the operation is denoted by a star between x of n and h of n. It's very easy to see that if I change the independent variable, let's call n minus k equal to r, then x of k, n minus k equal to r, so k would be equal to n minus r, and therefore this summation yk can be written as x of n minus r h of r. I've changed the independent variable, which is an integer. Now when k goes from minus infinity to plus infinity, what happens to r? R also goes from minus infinity to plus infinity, right? And therefore these 2 summations are identical. That is, this shows a very important relationship, that you can shift either the impulse, unit impulse response, or the signal, it doesn't matter. All right, the 2 are the same. In terms of mathematics notations, mathematical notations of operation, we can say that this summation is h of n convolved with x of n, and therefore the operation of convolution is commutative. That is, what you convolve with what, it does not matter. And in a similar manner, you can show that x of n convolved with h1 of n convolved with h2 of n. You can go on doing convolution of different signals. Well, you can show that this is the same as x of n. What you convolve with first, it doesn't matter. h2n, h1n, or you could even start with h1n convolved with x of n, then convolved with h2 of n. What does it mean? It means a very simple thing in terms of linear time invariant systems. Suppose I have 2 systems, S1 and S2, whose unit impulse responses are h1 of n and h2 of n. Then if I apply an x of n here, the output here shall be x of n convolved with h1 of n, system 1, and the output here shall be this input convolved with h2 of n, and therefore this output shall be x of n star h1 of n star h2 of n. All right. Now, convolution is commutative means that if you interchange the 2, the output shall remain invariant. That is, S2 can come first, S1 can go later. This also appeals to common sense, that cascading shall be independent of which one is put first. In practice, however, it does matter, because most of the physical devices are non-ideal. For example, if these are two amplifiers, then the signal level is important. One of them may saturate. But if there are no such non-idealities, then it does not matter which order we put the two systems. The essence of this discussion is that convolution operation is commutative. Convolution is also associative. This operation is also associative, which means that if you have x of n to be convolved with, let's say, h1 of n, which is convolved with h2 of n, then this is equal to, it doesn't matter what you do first, you can first convolve with h1 of n and then convolved with h2 of n. This is the associative property, and one can very easily show that convolution is also distributive. Distributive. That is, x of n, if it is to be convolved with, let's say, sum of two unit impulse responses, what kind of a system does this represent? We have already discussed parallel connected, that's right. h1 of n plus h2 of n means there are two systems which are connected in parallel. That is, what we have is this, in terms of block diagram, x of n goes to one system whose unit impulse response is h1 of n, the other system h2 of n, and the two outputs are simply added together. That's what it represents, y of n equal to x of n convolved with h1 plus h2. Now, you can, the distributive property says, it's very easy to show from the definition that this is equal to x of n convolved with h1 of n plus x of n convolved with h2 of n, which is what we have represented by this block diagram. The proofs are elementary, and therefore I omit the proofs. Just from the definition it follows. Now, enough of abstractness, let's see the mechanism. Let's see physically what is happening in the operation of convolution. It will also show you a simple way of visualizing convolution. Let's take this. Convolution is x of k, h of n minus k, summation k equals minus infinity to plus infinity. This is y of k. I'll continue to write this as many times as I can so that you don't have to hesitate as to what convolution summation is. Now, let's see physically what is happening. This is a discrete time situation. So, let's say k equals 0, plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. All right? It goes on this side because of limitation of space. I will not show any of them anymore. And to be crisp, to be concise, I will not write x of k as x bracket k. I will write it as a subscript, if you permit. We shall write this as x of k, all right, so that I conserve some space. Then what I do is I write the signals x0, x1, x2, x3. Then I write here x of minus 1, x of minus 2, x of minus 3. This is x of k. This line is x of k. Let's write h of k also below this. Try to follow this. h0, h1, h2, h3, h minus 1, h minus 2, h minus 3. what I'm trying to do is to visualize this convolution summation. All right. Now this is hk. What we need is, however, h of minus k. There's an h of n minus k. And therefore, what we do is, with this as the pivot, we flip. That is, this becomes h1, this becomes h2, this becomes h3, h of minus 1, h of minus 2, h of minus 3. Now suppose I have to compute y of 0. Y of 0, that is at k equal to 0. Then y of 0 is simply x of,
So it should be y of
I'm sorry, I beg your pardon. This must be y of n. All right, putting n equal to 0, y of 0 shall be x of k multiplied by h of minus k. Corresponding samples are to be multiplied and then they have to be added. So in terms of an operation, what we do is we multiply this to x0 is h0. We multiply x of minus 1 to h1. If k is minus 1, then it will be h of 1. We multiply x1 to h of minus 1. We multiply x2 to h of minus 2. We do this multiplication column wise and then add them up. All right. That will give me y of 0. Now, reduce this. We had x0, x1, x2, x of minus 1, x of minus 2, x of minus 3, and so on. This is x of k. And then we had h of minus k. H of minus k, we had h0. This was h of minus 1. I beg your pardon. I'm making a mistake again. This is h of minus k. So h of 1, h2, h3, h of minus 1, h of minus 2, and so on. Now suppose I want to construct h of 1 minus k. H of 1 minus k. What would happen to this? It would be shifted one position to the right. It is 1 minus k, not k minus 1. It would be one position to the right, which means that h1 shall come here, h0 shall go here, this will be h of minus 1, this will be, what will this be? h2, this will be h3. The whole thing shifts one position to the right, and therefore h4 shall come here. Now, if I multiply column by column, that is, if I multiply x0 by h1, x1 by h0, and so on, and add them up, what is it that we get? We get y of 1. If you see it carefully, y of 1 shall be equal to xk h of 1 minus k. K equals minus infinity to plus infinity. Let's take the central term x0, k equal to 0, h1, x0, h1. The other term, the previous term is x of minus 1, h. Yes? If k is minus 1, then 1 minus minus 1 is 2, plus the next term would be x1, k equal to 1, k equal to 1, then 1 minus k is 0, x1, h0, and so on. This is precisely what we get by multiplying term by term, column wise, and then adding them up. This is the mechanism. If we if we want y of 2, for example, y of 2, what we shall do is we will shift one more time to the right. That is, h0 shall come here, and then multiply column by column, add them up. This is also a practical method of evaluating the convolution. If every time you have to write this summation and substitute and so on, it takes much more time. Even on the computer, all that you have to do all that you have to do is to give a shift instruction, then multiplication column by column and addition. It saves a lot of time. Let's consider an example, a simple one. Let's say we have x of n is like this. We have a sample at -1, this is 1. We have a sample at 0, this is also 1. Then at 1 it is 0, at 2 it is 1, and at 3 it is 1. Let's say this is x of n. H of n, let's make it simpler. Let's make 2 samples, just 2 samples. One is, let's say, at 0, and the other is at 1. To bring variety into experience, let's say this is 1 and this is -half. All right. We have to convolve x of n with h of n. All other samples are 0. All other samples are 0 on this side, and so on. Okay. So what we do is we put values of 0, 1, 2, 3, -1, -2, -3, 4, and so on. We put x values first. X values are starts at -1, so these are 0, 0. -1 is 1, 0 is 1, 1 is 0, 2 is 1, 3 is 1, 4 is 0. These are the x values. Then I put the h values, h of k, all right. So at 0 it is 1, and at 1 it is -half. All other values are 0. Once you get used to it, you will find this as a very, very important, instructive operation. Now, I want to calculate x of 0. I want to calculate y of 0. Then what I do is, first I flip this over with 0 as the pivot. That is, I make -half here, 1 here, 0 here, all other samples are 0. This is what? H of minus k. All right. So if I want y0, if I want to calculate y0, then I multiply term by term, and the only multiplication is 1 -half, that is -half plus 1. So it is half. All right. Next, if I want to calculate y1, then I make one shift to the right, that is 1 -half, all others are 0. This is h of 1 minus k. So y1 shall be 1 multiplied by -half and 0 multiplied by 1, and therefore it is simply -half. All right, and then I can continue the process. This is what one would do if the signals are given like this and the number of samples is small. All right, can you guess what the total number of non-zero samples in y of n shall be in this particular case? Total number of non-zero samples in the output. There are 1, 2, 3, 4, 5, pardon me, and there are 2 here. 2 non-zero samples in h of n. Well, the general rule, you can continue this and show that the number of non-zero samples in y of n shall be the length of this. How many? The length, by the length I mean the number of non-zero samples. This 0 is not to be considered as a 0 sample, it's in between. So 1, 2, 3, 4, 5. There are 0 here, 0 here. 5 is the length of this signal. 2 is the length of this signal. Then it is 5 plus 2 minus 1. 6 non-zero samples. In general, you can conclude that if x of n is convolved with h of n, and x of n is of length n1, and h of n is of length n2, then the total number of non-zero samples, in y of n, where this is y of n, is capital N. This is equal to n1 plus n2 minus 1. You can rigorously establish this. The proof is elementary and therefore I shall skip. Let's take another example where the visualization is neither needed nor it makes things simple. And let's consider this example. X of n equal to h of n. Both functions are equal. And this is alpha to the n un. Now it doesn't say, well, it says that the samples in both x of n and h of n are 0 for n less than 0. Nevertheless, the length is infinite, from 0 to infinity. U of n goes from 0 n equal to 0 to infinity, and therefore the length of x of n, length of h of n, both are infinitely large. And you cannot go on shifting and computing. It is easier to apply the definition here. That is, what you do is y of n is x of n convolved with h of n, and this is summation xk h of n minus k equals minus infinity to plus infinity. Now you substitute. Xk is alpha to the k uk, and h of n minus k is alpha to the n minus k u of n minus k equals minus infinity to plus infinity. Now these two, alpha to the k and alpha to the minus k, they cancel. Alpha to the n, the summation is over k, so n must be a constant. You can take it out, alpha to the n. What remains inside is the product uk u n minus k. Now uk is 1 for k greater than equal to 0. U n minus k is 1 for k greater than equal to n. All right. So where does this product remain non-zero? 0 and no n. And what is the value of this product in this range? 1. At each point it is 1. So how many 1s are being summed up? N plus 1. And therefore the great conclusion is that y of n is simply n plus 1 alpha to the power n. Should we multiply this by un? Does the product, does y of n exist if n is less than 0? Why not? Why not? If the system is causal, then you remember the definition. X of t1 equal to x1 of t equal to x2 of t, t less than equal to t0, then y1 of t, y2t, t less than equal to t0. I would leave you pondering over this question. Should we include a u of n or not? I will not answer all questions. I will raise some questions and leave them unanswered. All right? When you ask a question, I will I'll take care. I'll try to answer. But some questions I'll leave. Should un be included or not? That is the question. All right? I think we'll stop recording here.